Hello everyone, can I get your attention? So we're going to start now. This is the IAP class Causal Inference in Deep Learning, so I'm sure you all are aware. So our GitHub repository is this website. Sorry, it's a little small, but I've also emailed it out. github.com/maxwshen/IAP-CIDL. So I just pointed that out because our notes for today are online. So yeah, again, my name is Max Shen.
And Fredrik, Johansson.
Yeah, and this course, right now we planned it for 3 days. I would describe myself as like an enthusiast, but not really a researcher in this area. So that's why I decided to organize this class, because I think it's really cool material. I'm going to start off today with like a 20-minute or so introduction to just how to think about causality for people who know some machine learning but haven't really thought about causality before. And I'm going to cover those topics, and then Fredrik is going to take the rest of this hour and a half. Do you want to describe what you're going to talk about?
Yeah, so we will focus on causal effect estimation today, like trying to estimate the effect of a treatment on an individual primarily, and the both causal and machine learning aspects of that.
Yep. Then tomorrow, Fredrik is going to take the first 20 minutes or so to finish his part, and then I'm going to take the rest of tomorrow. I'm going to be focusing on something called cause and effect discovery, or causal discovery. I'm going to describe what that task is more later. Then I'm going to structure that basically as like a review of a lot of different papers that have, proposed different methods for cause and effect discovery. So it's not to be super in-depth, but just like really broad over like a bunch of different papers. And then the last topic we're going to talk about.
On Thursday will be reinforcement learning. So this stems from the fact that me and my group, or not my group, but the group that I'm in, I've thought a lot about applying reinforcement learning methods to healthcare, and we're thinking about the both theoretical and practical challenges of doing so.
Yep, so that's the plan right now. There may be a winter storm tomorrow, so I guess we're going to keep you updated with the schedule, but that's our idea right now. So I'm just going to dive into my first 20 minutes or so. Again, just an introduction to that, how to think about causality. So first I'm going to be talking about statistical reasoning. I guess stuff that you all already know, and just to contrast with causal reasoning. Then I'm going to define something called structural causal models, and then explore what interventions mean in that sort of setting. So just to start with stuff that you all already know. So in a common statistical reasoning setting, we might have data, so like x1, y1 pairs up to xn, yn. And we might assume that this is distributed IAD from some joint distribution, which I'm going to call pxy. So this is our empirical data, and I'm going to call this collection of empirical data Pn of xy. So in this setting, one thing that we might be interested in, if, for example, y is the reals, we might be interested in regression. And that corresponds to learning a function, f of x, where you're just getting the expected value of y given x equals little x. Another thing we might be interested in standard statistical world is classification. So if y is just plus or minus 1, try to classify, and that's just f of x is the most likely value of x. Sorry, most likely value of y given x. In a more maybe exotic application in the statistical reasoning world, we might be interested in some sort of unsupervised deep generative modeling. So, for example, if x is images and y is captions, we might be interested in generating novel and realistic images and captions. So how that generally might work is you use a deep model to learn some kind of joint distribution called p hat xy, and then your samples are just x hat, y hat. And you hope that your generated images and captions are realistic. So you hope that you've captured something about the true underlying joint distribution. So what these examples kind of point out is that in the standard machine learning world, the joint distribution pxy is really like the master object. It contains all statistical information you need or that exists about your random variables. So just So to put this another way, if you have any sort of statistical learning problem, you can solve it by first finding a joint and then manipulating the joint to solve the problem. So given the importance of this joint, I'm going to frame a lot of the machine learning tasks as you're given the empirical version of the joint Pn of xy. You want to infer the true underlying joint P of xy. The issue is that this is an ill-posed inverse problem. What that might look like is if we have a space of empirical data from which we have a point, and then we compare that to the space of joint distributions. There's a one-to-many mapping here. So there's many possible true underlying joint distributions that could have given rise to our single observed data set. One way to motivate this is, for example, if x is the reals and we're in regression, then this is a picture that I'm sure all of y'all have seen before. So here's x, here's y. We have some observed data. We can fit a bunch of different curves to this, essentially. So we could fit like a really curvy curve. We could fit like a not so curvy curve, something like that, right? So this just highlights that there are many possible joint distributions for a single data set. So that's statistical reasoning. So for causal reasoning, I'm going to expand this picture, so I'm going to erase this. And consider a new space called C, which is causal models. So this is the joint, and this is data. There's again a many-to-one relationship here. So for a single joint distribution, there are multiple possible causal models that could have given rise to this joint distribution. Informally, there's a few ways to see this. Some phrases that you all are aware of already. Correlation does not imply causation. So if we have two variables, A and B, that are correlated, A could cause B. B could also cause A. We don't know which one of these is the case. It's also possible that there's another variable that causes both of them, that they do not cause each other. But in all these cases, A and B are like equivalently correlated. So that's something that you already know. Another way I can informally motivate this is if a joint distribution on A and B, I can break this up into two algebraically equivalent ways. But these two ways have slightly different, I guess substantially different causal interpretations. If you're philosophically willing to give causal interpretations to these, you could consider this first as B happens and then A happens given B with something. And conversely here, it seems like A would cause B instead. So what this is pointing out is that if you want to infer C from the joint distribution, this is again another ill-posed problem. So put another way, if you want to infer the causal model just from observational data alone, you need to solve two inverse problems. And that requires more assumptions and adds fragility to your problem. So cause and effect discovery, this is the task of trying to infer the causal model given observational data alone when there's only two random variables. So I'm going to be discussing that more tomorrow. Now, in practice, you're not always forced to infer what the causal model is. Sometimes in practice, or often in practice, you can assume things about the causal model. So we have a causal model that might look like this. This is a treatment. This is an outcome. These are X's covariates, such as age and so on. And so consider this as like a clinical trial sort of setting. Then we're assuming in a clinical trial that you apply the treatment and that's causing the outcome in some way. So a question of great importance here is trying to evaluate the impact of your treatment. And that's what's called a counterfactual, which is something that Fredrik is going to talk about more later today. So specifically what a counterfactual is the question, what would the outcome be if this given patient received the opposite treatment that did not happen in reality? So also a very interesting causal question. So I wanted to spend a little time to briefly give an example on two causal models that can give rise to the same joint distribution. So consider an MNIST data set where X is handwritten images and Y are labels of which digit they are. So this might be one causal model. So here Y is causing X. I'm going to give an interpretation of what this means first. But let me write out this. And I'm going to draw another causal model here just for comparison. So a scenario where this might be the causal model, for instance, is we have a human writer who is generating the handwritten image. And this process of the human writing is described by function g, where all of these n variables are just random noise. So it's a random process where g is a deterministic function. So in this, I guess, story, we have a human writer who's given a label. The label is generated by some noisy distribution, it doesn't really matter what. Then the human writer tries their best to try to write what that label says. And maybe there's some noise in this process, so the human writer is not perfect at observing what the label is, or has some problems with like executing motor functions sometimes, stuff like that. So it's a noisy process. That's what might be happening here. What might be happening here is z is a latent variable, and I might call this an intention. And here we're asking the human writer, first come up with a number in your head, then do some data entry and write down what that label is, and then also handwrite the number, again, to produce X. And again, both of these processes might be inherently noisy. So the human might not be perfect at data entry, and the human, again, might have some trouble with executing motor functions sometimes. So these are two causal processes that generate X and Y, where the joint distribution X and Y can be the same, even though they're generated by different causal models. So the next question I want to answer is, what's the impact of these different causal models? And the impact is that they will give different conclusions when you ask about the impact of interventions. So if you, before I go there, I want to point out this very important notion of a causal assignment. So here, this arrow is not algebraic equality. So algebraic equality is a symmetric operator. Causal assignment is an asymmetric operator. You can also think of it as like equal sign in the programming. Left hand side, right hand side are different. So if we were to think through what might happen if we were to intervene on the causal generative process for the label Y, then you can see what might happen here. So consider that we intervene on this and we intervene such that y is being generated from some distribution I'm going to call f of like 9, like the digit 9 of n of y, and this is just like a Dirac delta point mass on the digit 9. So in this case, the generated data set y and x, the images are going to be affected. In contrast here, if we do the same intervention, then y is, let's see if I should, f of 9 with some noise. Now y doesn't have a parent to z anymore, so this graph looks different. And when you do this intervention, the images produced are not changed. But here the images produced are changed. So that's an example of that. So I wanted to more formally, but still very informally, describe what a structural causal model is. I feel like for this crowd, if you want more details, you can go to the notes and textbooks and so on. So we might generalize what we just saw and say that an SCM, or structural causal model, so a structural causal model, as we saw, is a DAG of D nodes, maybe, where we have this property. So for x of j is causally assigned as a function f of j of its parents, and some noise j goes from 1 to d. With one more condition, and all n have to be jointly independent. So that's my very informal definition of a structural causal model, but hope you see how it captures the structure that we just saw. So how we are going to define interventions, as we just saw here.
Excuse me. What does the parent mean? Parent of X?
So in a DAG, the parent, I guess this, so every time you have a structural, causal assignment, you would have a directed arrow or edge between these nodes, and just have the parents in the graph. So an intervention might look something like this, where within an SCM, we replace some of these xj causal assignments with really whatever you want. And I'm just putting tildes to indicate that. And we still have the same conditions. Mathematically, you might want your intervention to still preserve that all n's are jointly independent. You might also want to preserve that your graph is still acyclic, but that's mathematically up to you, I guess. So one important type of intervention is called a hard intervention, and that corresponds to setting x of j just to be a point mass. So it no longer has any parents and is independent of its parents or original parents. In contrast, the soft intervention might preserve some or all of the original parents. And what it might do is it might change f, or it might change the noise. So those are interventions. Lastly, I wanted to talk very briefly on how you might calculate the impact of an intervention. So again, this is important if you're in a clinical trial setting and you want to see if your treatment has any impact. So how I'm going to describe a hard intervention is through this notation. So maybe we're interested in the outcome y given that we intervene on X. So I'm not really referring to any specific graph I drew before, I'm just positing these names. So by this do notation, I'm referring to a hard intervention. So this just refers to, so I'm going to use this for causal generative process, what that is generating X, is intervened to a point mass. On X. So in this setting, we're given an SCM, and we want to try to calculate this. So what is this equal to? With this intervention, this is in causal language, and what would be nice is if we can equate this to objects that are purely statistical objects, then we can just calculate it as normal. It turns out that you can't do this unless certain conditions are satisfied. You essentially need to control for confounding variables, and there are a couple criterion for what set of confounding variables are sufficient to control for to be able to calculate this just using pure statistics. So I'm going to give you two criterion. There's way more. One of them is called the backdoor criterion. So a set of variables S is sufficient for, we call this problem identifiability. Sorry for my bad handwriting. And again, by identifiability, I just mean, is it possible to translate this into purely statistical objects? If it is, then it's identifiable. Then if there's a couple conditions. So first, no node in S can be a descendant of X. To calculate that. And second, S blocks every path from X to Y with an arrow into X. So you can sort of visualize this. Both of these criteria combined together means that S needs to not be between X and Y, but needs to block paths that kind of go around the backside of X. That's why it's called backdoor criterion. So in such a situation, then you can write this intervention by controlling for variables in S. And that's it. So what's nice is that both of these are purely statistical objects. So if you have enough observational data to get these things, then you can figure out what the causal impact of an intervention would be. But remember, that's assuming that you have a specific SCM. And in reality, you might not have the true SCM, so that's a bit more complicated. The second criterion that I'm going to very briefly introduce is called the disjunctive cause criterion. So it's basically just going to replace these two with another condition. Everything else is the same. The only condition you have to satisfy is that S is all direct causes of X, Y, or both. So it's a bit conceptually simpler than the backdoor criterion. So this is really nice. Usually determining the impact of an intervention is kind of a really important question in causality. So being able to reduce it to statistical objects is very nice. But again, we need to control for some confounding variables, which are called S. So when the SCM is not actually known, And the true escape might be different than the one you're assuming. Something nasty that can happen is that you have what's called an unobserved confounder. In such a case, then it becomes extremely tricky and possibly just impossible to equate this to anything. Usually the best you can get is a bound on what this object might be. So the assumption of no hidden confounders or no unobserved confounders is a common one when you're doing theoretical work in causal inference. So that's my intro. Now Fredrik is going to take over. Yes?
A direct cause in the graph is just the parent, right?
Yes.
All right, thanks for that intro. It'll make my life a lot easier.
What's that?
Yeah. Let's see this. All right, so I'm Fredrik. I come from something called the Clinical Machine Learning Group over at the Institute of Medical Engineering and Science here at MIT. And I've been working in this space for the last couple of years doing research, and most of the sort of questions that we deal with in the group are somehow connected to either healthcare specifically or through some sort of causal question that we're interested in. And most of the questions that we talk about have to do with making decisions. So that's what I will be focusing on today. I will not be talking so much about graphs, but we'll connect a little bit to what Max talked about in the intro. And the reason I wanted to talk about these things specifically in this course, and I was very happy to see Max organize it, is that the causal inference problems that we think about are becoming machine learning problems more so than statistical problems. And one of the reasons for that is that the data that we deal with increasingly is very high dimensional. So if you want to ask about what is the effect of a gene on a specific phenotype or some kind of property of a human, the data that you deal with is the entire human genome, and as you know, that's a quite high-dimensional piece of data. Another aspect that is very nice for machine learning models, but not so much for statistical models, perhaps, is that we get huge data sets these days, predominantly observational ones, and I'll explain what I mean by that later, but you can think of it for now as just non-experimental data sets. So it's not a clinical trial where somebody has assigned perhaps randomly treatment to individuals, but rather it's just whatever data was available. So that could be the health records of patients in hospitals, or for example, how users interact with advertisement on websites. And last but not least, something that machine learning is good at is personalization. So we've seen for the last couple of years that very, very high capacity models have been able to learn interesting things using, for example, deep learning. And a question that we might ask is, how should we teach our students so that as many of them as possible achieve the highest possible results? So this is a question that appears in online education, for example, where you might ask which problem set should I show to a specific student so as to maximize their probability of passing the class. And specifically for me, decision making is a lot about healthcare questions. And so a lot of the healthcare questions that we think about are of this nature, and it might be who should receive which treatment. That's an important one. It might be that different medications for diabetes work differently well for different people. So we want to choose with good accuracy the best one for each. Which lab tests should be ordered? Lab tests are often expensive and might be invasive, and we might not want to run every test on every individual, of course. And the last one, we could ask, when should we intervene on a patient? If we're performing a surgery on a patient that is in critical condition, we might want to wait so that they're stabilized before we perform the surgery, or maybe it's crucial to intervene immediately. And lastly, I just put what was the cause of death, which is not technically a decision problem, but certainly a causal one that we might be interested in. So to make some of these a bit more precise, I will give the example of Anna, who's a patient who comes to the hospital. She's 54 years old, an Asian, and she has high blood sugar. Another way to say this is she's diabetic, most likely. And we're wondering, how should we best treat Anna so that we can reduce her blood sugar levels? And we have to our as options, we have two different medications that we can consider, medication A and medication B, and we want to know which is the best one for Anna specifically. So to illustrate the problem that we're facing, we can think of these like two separate paths in reality, in this sort of sliding doors situation where if we go down medication A, we will observe some certain blood sugar level at September 15th, and we will call that Y0 for the outcome under medication 0. And if we took the other one, which we'll call treated, we will observe Y1. And importantly, we can only observe one of these for every patient. We will pick one medication and stick to it. Typically, it's not the same thing to try out both simultaneously as it would be to try out one versus the other. So we'll think about this choice a lot today. And we will care about something called treatment effects, and Max talked a little bit about this before. Specifically what an effect will mean, or an impact, as you call it, in our case, will be the difference in these outcomes. The difference in blood sugar level on September 15th, where we could go down either of these two paths. And this can be used to ask population-wide questions, such as, does smoking have an effect on cancer rate? Or a personalized, individual question, which medication is best for a specific individual? So the point of this talk is largely to connect these types of questions with eventually deep learning, but perhaps machine learning in general first. And a machine learning approach to this problem would be to try and predict what would happen under both of these two outcomes. And we will call them potential outcomes because we're not guaranteed to see either of them, but both could happen. And so if we take the machine learning approach, we would say we predict y hat 0 and y hat 1, and we compare the two in order to give the most optimal treatment. And in this case, talking about blood sugar, perhaps we want to reduce it. So if y hat 0 is smaller than y hat 1, we give treatment 0, and otherwise we give treatment 1. Seems sensible. And what we could do then is to collect a bunch of data and learn from it. So here we have a very simple data set. We have a single feature X that I sometimes would call context, and this is what describes an individual patient. It could be a person's entire health record. It could be their genome, things like that. But let's keep it simple for now and keep it one-dimensional. We will record also the treatment that they received. So think about this as a set of records of patients in the hospital that we had no control over, a set of observational data. So this was given to us. We don't know how it derived or arose. Okay, so we have age and we have treatment, and then we have some outcome, which was the blood sugar level at some point after treatment. Okay, so we try to fit some function to predict y from these other two variables, x and t. And this is superficially, or this problem is very similar to other types of machine learning problems that we know, and we know machine learning works well for. So imagine trying to put a label on an image, for example. We could say that this is a cat, most likely, by what is said in that signal. So I just made this up. I don't know what actually is said in that example. But anyway, we try to match features to labels in some way. So the problem for us is that, well, this is superficially similar, but actually what we care about in our example is two different labels, right? We care about what would have happened under the treatment that was prescribed, and that we kind of know already. But we also care about what would have happened under the thing that was not prescribed, the counterfactual, as Max put it before. So if, say the first row again is this patient Anna, and she was given treatment B, we want to know what would have happened under medication A. And that's necessary in order to estimate the effect of the treatment. Remember, the effect was the difference between these two quantities, so we need to impute the one that we don't observe. And so that means that we have this kind of missing variable problem. We don't observe all the data that we want to learn from, if you know what I mean. So there's one type of label that we will never have supervision for, and that makes it different from supervised learning. So you can think about it, as I mentioned, as a missing variable problem. That is one label that we consistently never observe. But you can also think about it in terms of a domain adaptation problem, and we'll get to that perhaps more tomorrow. But the point will be that we learn what would happen under treatment based only on people who were actually treated, but we want to predict for people who weren't And that makes it a generalization under a distributional shift or a domain adaptation problem. Okay. So how many here have taken a machine learning course in their life, by the way? Okay, good. How many have heard of the phrase domain adaptation before? Okay, good, perfect. Nice. So another point here to be made is that unlike, for example, the, let's see, can I go back? Yeah, unlike the pixels in an image of a cat, we have a very, very specific or significant feature in our set that is different from all the other ones. So sure, these two pixels have about the same impact on the classification of the image, but really for us, we care a lot more about the treatment variable than anything else, because we want to know what is the effect of the treatment. We talked before about interventions, right? And the intervention on X in the case of Max. Here, what we're interested in is the intervention on T. What would happen if we went in there and treated a certain individual who wasn't treated before? So we really don't want to lose the information about T in any method that we might use to learn these counterfactuals. So if you think about using a variable selection procedure, you should probably avoid throwing away the treatment variable. Okay. So this is sort of, so far I've only talked high level about what we want to achieve in this lecture. And this is, I'm just finishing up this little intro here by a slide that I borrowed from Judea Pearl. And he showed this recently, I showed it before, but there's a conference called NIPS in the machine learning community. And he gave a talk there in a Causal Inference workshop. And basically the gist of it, he criticized machine learning a lot. For machine learning, they don't care about causality, those guys. And the reason, or the way he expressed that was to show the slide and say that all of this is what we should be doing, but machine learning only does this little thing over here. And that's kind of largely true. So I'll take you through it a little bit. This over here is the data, the joint distribution that Max talked about before, right? We have the causal diagram that expresses which variables cause which other variables. And these two together specify the structural causal model. Now, this part here, the query, represents what we want to ask about the model that we produce. And in my case, it will be what is the effect of one variable on another. And then finally here, we try to estimate that function, essentially. So sure, machine learning does a lot of this, but as Max will show in his talk tomorrow, actually there will be a lot of this from the machine learning community too. And I will be talking primarily about these two things. What questions should we be asking, and what functions do we need to estimate in order to answer them? All right. So I will not be using the structural causal model framework. I will introduce something else, which is convenient in certain settings. And that's called the potential outcomes framework. That will be the first part of this hour or so. I will then move on to supervised learning and risk minimization and show how those two things relate. And I will probably not get into the third point today, but tomorrow we'll be talking about adjusting for distributional shift, which is a sub-problem in these other two. Questions so far? Right. Okay, getting back to the example of Anna, the patient in the hospital. We can visualize her data in another way. So I am going to use the causal graph for a second. Anna's causal graph we can think about like this. She has a health record X that describes her previous conditions and so on, and perhaps whether she's diabetic or not, that would be useful. And that in turn causes which medication she is prescribed. If she is already diabetic, she will be treated differently than someone who's not. So we can assume that the health record crosses some treatment or some medication, and also her preconditions will cause or have an impact on the blood sugar level that we observe. But the thing that we're really interested in this arrow is this arrow here, which is the effect of the medication on blood sugar. Now, this is what we will call a confounder. It's something that affects both the outcome that we care about and the treatment. And the reason it's called a confounder is that if we don't adjust for this, we might draw the wrong conclusions about the effect of T on Y. Yep.
Why does the health record have medication?
Because the doctor makes a decision about how to treat based on the record. Yep. So it might be some things are dangerous to combine, or a person who had a surgery or something like that. I don't know. But this appears in a lot of different settings, not just in medical setting. I know I've been talking a lot about it, and I will keep doing so a little bit. But you can think about job training, for example, in which you're interested in the effect of job training on the future earnings of an individual. So the education level of an individual might impact his or her chances of receiving job training in the first place, and it will also impact the future earnings of that person. But we're still just only interested in this kind of error here. Yep.
Yeah, so I'm just sort of curious, in general in these models, if you have unobserved confounders, how screwed are you?
Well, it depends on the nature of it. I won't have time to get into a very good answer on the slide, so I might as well answer you now. What you can hope for is that you have proxies for these variables. So you have observed some noisy version of them, or perhaps you can infer them based on the data that you do observe. That's one approach that you can take. So essentially, if we haven't made notes in our health record that this patient is diabetic, perhaps we can infer that from all the treatments she received or all her previous measurements. So that's something that you can do. In general, it's hard to say. It's hard to say, but without making further assumptions. So as you'll see, and we'll get to more concrete assumptions later, you can't really do causal inference at all without assumptions. And we'll see tomorrow a couple of different ones for how you can infer the causal structure. Here I will assume that the structure is known. So that's an assumption I'm making too. Is that okay? Okay, cool. Lastly, you can think about advertising, where you're interested in the effect of an ad campaign on the sales of a product. So this type of structure, X, T, Y, appears all over the place. And that kind of, makes the graph a little useless. We know the graph already for these types of problems. So we can think about the quantities that we're interested in a different way. And I will use something called the potential outcomes framework, which applies to more general settings as well, but I'll use it only today in this kind of triple context treatment outcome scenario. It's also called the Neyman-Rubin causal model after the inventors. And we will let y parenthesis t denote the potential outcome under an intervention t. So this is different from a conditional, and we'll see that in a second. But essentially, this yt should represent what would have happened if we intervene with t equals t. Okay, so we just think of these as somehow complementary to causal graph. They're not exactly equivalent in any way. But these are very useful for the types of problems that we've talked about, the causal effect problems. And maybe you noticed already, but I say treatment a lot, or intervention sometimes, and I will use these completely interchangeably. There's also a word action that is used sometimes, specifically, or especially in the reinforcement learning community. And all of these, I will mean, with all of these, I will mean this T, the intervention or the treatment T. Okay, so we use potential outcomes to differentiate between conditioning and intervening. So a conditional outcome, for example, here, we could say, what is the average outcome conditioned on t equals 1? So that would be, what is the expected outcome for subjects who we would currently treat with t equals 1? If we follow standard practice in the hospital and we treat as normally, this is the data that we observe, and this is the average outcome of that kind of treatment. But that will not answer what is the effect of treating these individuals by comparing, say, this quantity and the quantity where I replaced t equals 1 with t equals 2. Those things will not answer or represent the effect. And we'll see an example of why that is later. So instead, the potential outcome, we should think of as what is the expected outcome if we were to treat everyone in this case, because we have a 1 here. So not just the people who would get normally treated, but everyone in our population. Okay, questions on that? It's the similar story that he told you before about correlation equalization. So I thought a fun way to illustrate this is through something called a Causal Jan. So this is a paper that came out last year, I think. And they illustrated the difference between conditioning and intervening by generating faces with mustaches either conditioning on the fact that the face should have a mustache, or intervening and placing a mustache there. So if you've heard about it, generative adversarial networks are models of, or ways of learning distributions, essentially. So in this case, we have observed a bunch of celebrity faces, and we want to learn what is the distribution that gave rise to these faces. And then once we've done that, we generate a bunch of samples of new random faces. So what they did was they said, okay, I want to compare what is the how would faces look if I condition on the subject having a mustache. And that's the bottom row here. And you can see that it's only men in this row, I think. I haven't actually yet. Okay. And so this would be what we expect from a conditional statement, right? Because most men, or it's mostly men that have mustaches. Whereas if you intervene, you expect the distribution of faces to be the same, but you put a mustache there. And that's kind of another way to illustrate the difference between conditioning and intervening. I'll leave for you to judge whether there are women or men in the top row. I'm not going to go into that. Okay. So to really, really hammer home this point, these are the two potential outcomes that we will be looking at today, the two outcomes under the different paths of this choice. Okay, so I'll be introducing some notation now. We will always in this talk be making the assumption that the treatment is a binary choice. Of course, there are tons and tons of applications where that's not true, such as if you have a dosage that you want to control when medicating someone. And we would call the event t was 0 the control, and t was 1 the treated for historical reasons. And y1 the treated outcome, and y of 0 the control outcome. So these are the potential outcomes. We have the factual outcome, which is the outcome that we observe. And that is the potential outcome corresponding to the treatment that was given. So we assume that if we give treatment t was 0, this will be 1, and then we will observe y at 0. All of these variables are distributed according to some distribution key. And specifically today we will be talking about two different kinds of effects. This is the first one. It's called the conditional average treatment effect. And it's simply the difference between potential outcomes conditioned on a set of variables x. And x in our case, we'll be thinking about the description of a patient or an individual. Now, of course, several individuals might have the same representation. So this will average over that. There might also be some noise in y. It might be that we can't perfectly predict the outcomes conditioned on x. So that would also be averaged over. And tau would be the average, the difference between the two. And this can be used to personalize treatment. If we have this for every individual in the data, we could say, what is the optimal choice for this person, or for a person with these features? Yeah, so simply by looking at the sign of tau, we can judge which is the better treatment. The second thing that we will not so much care about, but a little bit, is the average treatment effect, or the population average treatment effect. I will be using the notation 8 for that, and it's simply removing the conditioning, or averaging over all of the x's. So this is more of a population type query asking, is there an effect of smoking on cancer rates, for example? And this has been studied for a long time. And it's still going on. People are coming up with new fancy methods of estimating this thing under different conditions. And the assumptions that we need to make this possible at all to estimate are, well, behind this thing, or similar versions of it. He was talking about the backdoor criterion. Since we know the graph here, we don't need to infer what the errors are, but we will need some assumptions of a similar nature. And yeah, so this is often the target of dry trials. Okay. Right, so going back to our table. We have some records of patients like this. We can choose instead to visualize that on a two-dimensional plot like this. I'll put the context or the features of a patient here, x, and the outcome of an experiment or the intervention on the y-axis there. I will use color. I hope everyone can differentiate between the two. Typically blue will be higher up. That's another way to tell. Blue will represent the control population, the people who receive treatment A, and orange the treatment population, those who received medication B. And we can fill out a nice plot like this, and we can see, okay, there is some relation between age and the outcome, and there's also some relation between the color or the treatment and the outcome in this case. And I made a note up here saying that, well, these appear to be different somehow. There are more blue people to the right. Blue people are older on average, and we'll see why that is important later. But importantly, all of these points here, since they came from the database that we had, the electronic health records, for example, those are instances of the factual outcome, or samples of the factual outcome. So in order to estimate the effects that we cared about, both the 8 and the Kate, as you'll remember, were defined in terms of the potential outcomes, y0 and y1, and here we observe only one of them. So we would like to infer the counterfactual. If we had this, we could compute the difference between the two things, the difference between the counterfactual and the factual, and that would tell us what is the effect of treating this individual. And what would be very nice is that if we could have functions for both y0 and y1 for everyone, and that would leave you with something like this. These will be the expected outcomes condition on x, and this will be the primary goal of everything we will be doing from now on. Any questions about these plots? Great. So, from these, if you had the orange and the blue lines here, the expected outcomes condition on x, you could just read off the Kate, the conditional average treatment effect, as it's just the difference between the two. Now you might also think, since I have the samples, I can just read off the average treatment effect. I can just take the average of one group and then the average of the other group and compare them. Or no? No. Why not?
Because some are different ages. They have different priors. So you give people in one group a medication and it doesn't have much effect. You give people in the other group medication, could have a different effect.
Perfect. Perfect. Exactly right. So yes, I mean, I'll illustrate it in a different way. Or this is one alarm bells should be ringing here. We see that the conditional effect is always smaller than the average effect in this example, which that can't be right, right? And the reason is exactly what you said. So the blue population is typically older than the orange population, and so there's confounding. The age variable impacts not only what group you are placed in, but also the outcome itself. So these are actually not, in fact, the age or these conditional, expectations. So don't remember that part. Remember this part. Okay. Right. So what we computed, in fact, were these two conditional expectations: the expectation of the outcome in the treatment group and the expectation in the control group. But what we wanted was the expectation of the potential outcomes. And here you see again why these two things are different. The two potential outcomes are in fact defined for anyone, right? And the entire span of x. So we would like to evaluate that for the whole joint, both the blue curve and the orange curve. But the thing that we averaged over was only one of them. And that's why we get the wrong inference. And another way to see that is through something called Simpson's paradox, where even though this orange line is always below the blue line, so this will represent again the potential outcome condition on x for the treated and this for the control. Even though the orange is always below this one, the average of the orange is over this one. So we will actually conclude that the sign of the average effect and the conditional effect is reversed in all cases. And we can't have that. That's not going to work. So the reason for why this happens, as I said, is that this variable x is a confounder. X is here. X affects both the treatment variable and the outcome variable. And that means that it will confound the naive estimate of the treatment effect. The naive estimate being simply the difference between the two means. So what can we do? Any suggestions? What can we do? How can we get rid of that?
Can you get the joint of xy condition of t first?
Joint of x, t, y condition t.
Yeah.
So you're saying p of x, y condition t.
Yeah.
To do what?
And then integrate out afterwards?
Okay, it might be, yeah, you might be touching on a solution. Yes. Okay. Uh-huh.
It's a condition on that.
Yes, exactly. That's what we will do, and maybe that's what you meant as well. That is something that we will get to in a minute. If you have the opportunity, though, you should probably do something like this. Randomized control trials. That's why this is used in every clinical trial ever. You simply don't let t depend on x. Okay? So I know we've been talking about observational data, so I'm cheating a little bit here, but I thought I'd show it anyway. So if you have the option of simply flipping a coin for every individual and saying if the flip comes up heads, you give treatment 1, otherwise you give treatment 0, then that would be amazing because there would be no link, as you can see in the causal diagram, between x and t. And then this naive estimator would simply just work. You could just take the difference in one group, or sorry, the expectation in one group and subtract it from the other. Okay, so I just used this to illustrate the difference between them. One way of thinking about clinical trials is that the treatment assignment is simply randomized. It does not depend on the features X. Another one is to say that the two groups, groups of patients X conditional t equals 1 equals the groups of X, or distribution of X conditional t equals 0. This is not true for observational data. And so instead we have to do something else. And I'll just make the point that typically randomized control trials are very expensive. So that's one reason that we don't really want to do them. It might be both problematic to convince people to enroll in a randomized trial, or it might be just unpractical or unethical. So the example that is typically given is that we can't really force people to smoke and then see what happened to them 20 years later when they have cancer. And another reason to not use randomized data is that we have so much observational data. Almost all data that is collected is observational, in that we store health records every day. What happens to patients in hospitals? What products are bought on Amazon and so on. So it's very cheap and plentiful, and we should really be using this. So, in order to be using that, we will get to the conditioning on X in a second. But we'll need some assumptions in order to make it possible to infer the effect of t on y in the observational setting. So these are three very, very common assumptions that are used in causal inference research and practice, I guess. And these are sufficient conditions for identifiability. They're not strictly necessary in that it might be that we have the proxy scenario that we talked about a little bit before, which would violate the strong ignorability. But we'll get to that. So, strong ignorability says that the two potential outcomes, y0 and y1, I've switched notation here, apologies for that, should be independent of the assignment of treatment conditioned on the features x. So if there is such an x, the adjustment method that was proposed in the audience will work. So that means that no matter what treatment you were actually given, the same thing would have happened if you got the other treatment. That's what that is saying, essentially. And another way to think about that is to say that there are no hidden confounders. There's nothing that we didn't measure that impacts both the treatment and the outcome. We'll show an example on the next slide. Another assumption that is typically made is overlap. And that says that any treatment should be possible for any unit in the data. And that could be a very strong assumption. For example, if you have a rule that doctors obey, saying that if the blood pressure is over some value, I will give medication A, and I will go to medication B, I will never have overlap. There will be zero probability, well, almost zero probability, that both treatments are assigned to, or possibly to assign to each patient. But you can think about it in a slightly different way. For every unit X that we want to make inferences about, we need this to hold. So it doesn't necessarily have to hold for everyone, but then we couldn't say anything about the effect for everyone either. Okay, last one, which is an interesting one, I think, is called the SUTVA, or the Stable Unit Treatment Value Assumption. And it says that the treatment that I'm assigned is independent of the treatments you're assigned, and also the outcomes are independent. And that is not always true either. Typically in machine learning, in general, in statistics, I suppose, we make a lot of IAP assumptions. All our samples are independent, but this would be a case where that is not true. And the reason that might happen is if you think about vaccination, for example. So if I'm vaccinated, you're less likely to get the flu, which is nice for you, I suppose, although we don't interact too much. But not only that, if I'm vaccinated, maybe you're more likely to get vaccinated because you think, oh, that guy, he got vaccinated, so I should probably do that too. So that's something that you have to, this does not fall in that scenario. And that opens up a whole other area of research in causality because people really care about what is the impact of vaccination. Okay, so first, a few slides on ignorability. So ignorability was this first condition that we had, saying that we have no hidden confounders or that the potential outcomes are conditionally independent of the treatment given X. And this is meant to illustrate 3 different cases of ignorable causal groups. So here we have a confounder X that we observed, and then we have a unmeasured variable U. Here U impacts only the outcome Y, and here U impacts only the outcome T, and here we don't have any unmeasured variables. So in all of these 3 cases, we have no hidden confounders, because anything that's a confounder we measured, and anything not measured is not a confounder. So in all of these cases, we can estimate the effect of T on Y, and also the conditional effect that we talked about before, the conditional average treatment effect, conditional X. Those are all fine. As you may have figured out, we will not be able to perfectly predict Y in this case, because there's something that impacts Y that is not measured, but on the other hand, we can still estimate the effect of T, which is the crucial part. So you can imagine this as being wrong on, for example, the scale of Y, say that this is the truth and you estimate here, but for the 2 potential outcomes, you will consistently if this is the effect on truth, maybe this is the effect that you estimate. So even though you're wrong about the scale or the shape, you will be right about the difference in potential outcomes. I don't know if you can see that. Okay. Now, so what's a non-ignorable setting? Well, it's when we have an unmeasured confounder that impacts both the treatment and the outcome. And that was what the question was about before. And these are very real problems. You want to estimate the effect of some treatment, but you didn't actually measure everything that impacted the choice of treatment itself. And so a somewhat silly but still realistic example is where we collect a bunch of data about some patient, but we forgot to measure something very important about them, such as whether they were diabetic already or not. And albeit, although this seems silly, this happens all the time. And it might be just because we don't have access yet to the decision or the record of something that happened in an earlier stage in the hospital. So if it's a critical care setting, it might be that we haven't yet put a diagnosis, and if we had access to it, this estimate would be something different. Another problem where this appears is with compliance. So actually what you care about is not so much what is the effect of a treatment assignment, but rather you're interested in what is the effect of treatment compliance, if you take the medication or not. And that is something that you typically don't observe. And it might be that you have some side effects of a medication that you're given by your doctor, and then if you're enrolled in a drug trial, you might stop taking the medication because I get some side effects. So the side effect both will impact my outcome because I stopped taking the medication, and also, of course, whether I did take the medication or not. So that could be a very problematic situation. And that, again, is a whole other research area of its own. So we will assume that we are not in this scenario. We measured everything that matters. Okay, so finally, it can be shown through something called the adjustment formula, which is only a couple of lines of derivations. I won't do them here. Actually, if you are very interested in this topic, there's a nice tutorial by my co-author, Uri Shalit, who gave this tutorial at ICML a couple years ago. So you can go to his website if you want, and he has a proof in the slides of this thing. So it's a very simple thing. Well, if we have the assumptions that I made before about ignorability, etc., it will be true that the expected potential outcome, conditioned on a feature x, for which ignorability holds, is equal to just the conditional. So remember we said that conditional outcomes are different from potential outcomes. Yes, that's still true, but here we're conditioning on or adjusting for the confounders, every observed confounder. So great. Now we are back in the statistical quantities land. We don't have to think about these foreign causal quantities anymore, but rather we can stick to estimating conditionals. And specifically, if we're interested in the average treatment effect, what we should do instead of what I did before, simply taking the treatment group means and subtracting them, we should estimate conditional means. So think of this as a regression. We're estimating the outcome conditioned on some feature x for the treatment group and doing the same for the control group. And then we extrapolate to everyone. So for these quantities are only computed over half, say, or part of the population, but we compute this difference for everyone, and we take the mean of that. And that will be our estimate of the average effect. In doing so, will leave us with a consistent estimate of the average treatment effect. Questions on this? Good. As you might have realized already, it doesn't just give us 8, or the average treatment effect, but it also gives us Kate. Because these two lines that I showed you before are exactly these two conditionals. So computing the Kate simply is subtracting the 2 again. And whatever's, the only thing that's left for us to do is to estimate these two things. Or, yeah, exactly, this conditional here. And as it happens, that is something that machine learning is pretty good at, and deep learning in particular. So this takes us to the second part of this lecture, which will be on supervised learning. And I'll try in this section to illustrate why it's a reasonable thing to do, and then why it's maybe not so reasonable thing to do after all. And I'll try in the last part tomorrow to sort of, iron out the little kink there. So, as I showed you before, a lot of machine learning problems are the supervised kind, where we are shown some input features x, and we are asked to predict some label y. And that was, we had the examples of cats, and labeling images, and the speech recognition example as well. And for now, we can think about our treatment as being part of this x variable. Now, I said you shouldn't do that before, because we don't really want to lose t in a variable selection procedure and things like that. But we will make it specific later how t comes out for causal effect estimation. I'm just going to introduce common things in supervised learning. So we assume that we learn from n samples drawn from this joint distribution of x and y. Okay, so what we want to do a lot of the time is to find some function f that predicts this conditional expectation of y given x well. And it's often done using something called the risk minimization principle, where we define a loss that we care about, in this case the squared loss, saying how far off are we in our prediction age from the observed outcome y. It might be something like the log loss or the 0-1 loss for classification. Now, our job is to find the minimizer of this risk. So if you think about regression, we want to fit the sort of mean, the least squared error line or curve fitting our data. And as you know, typically we don't observe this expectation. You can think of observing this expectation possibly if you have infinite data, but that's rarely the case, even in observational settings. So we will instead have to rely on something called empirical risk minimization. And the goal here is, instead of minimizing the risk in terms of the expectation over a distribution, we will have the empirical expectation, or the mean loss that we observe in a sample. So in standard learning theory, most of you had seen machine learning, so I'm assuming you're aware of this. You can make these types of bounds, saying that actually, if you observe enough samples, the empirical mean is a pretty good estimate of the risk of the population. Now, of course, this model complexity term here that I kind of didn't mention will impact how quickly this happens, but in sort of general terms, we can assume that this will give us a reasonable estimate of the conditional expectation. Okay, so deep learning. It's in the title of the course, and it's something that I've been using for the last couple of years to do causal effect estimation. And when we started doing this, people were, well, I say they were skeptical in the start. They're still pretty skeptical. But what we observed is that the most methods that were used in order to estimate causal effect were either linear models, or some of them were using decision tree type models. But we know that these are not appropriate for all settings, right? And we know that a lot of functions that we care about can be learned using neural nets. So why not try that? So the talk tomorrow will touch upon why is specifically neural nets interesting for causal effect estimation, and why are they suited, or, well, why are they particularly well suited for dealing with some of the distributional shift issues that I'll raise at the end of this talk. Of course, I should mention that, I mean, I gave a sort of hand-wavy argument that if you do empirical risk minimization, you'll get something nice in terms of population risk, but people are very divided on how this actually happens with neural nets. I don't know if we have any deep learning experts in the audience. Anyone brave enough to raise their hands? Okay, you'll agree with me that people are divided, no? So the reason being that it's very easy with a deep neural net. If you make it big enough, you will have zero empirical risk, and no one typically believes that you have zero population risk. So my bound didn't really make sense. Then I guess maybe we have a large capacity term or something like that. But still, we generalize much better than we expected with these things. And that's, I mean, that's not for me to solve in this talk, but I think that's something to bear in mind, that the standards of learning theory that we learn in the classes typically don't apply for things like deep learning. Cool. All right, so our goal is still to estimate potential outcomes, because we had these two conditional expectations before, not just one, and now we let the function that, or the hypothesis that we care about, be a function of both x and t, and we want to learn the conditional expectation not just of y given x, but y given xt, because we said under ignorability and overlap in these things, this will equal the expected potential outcome under this conditioning. So we can repeat the risk minimization idea, right? I mean, we let each hypothesis here of each potential outcome, so this would be the outcome under control, or an estimate of it, and this is the outcome under treatment, and we can minimize these equivalent risk objectives that we had before. So that's all well and good. Maybe? Why would this be hard? Any feeling on this? What was the step that we took last time? We went from this to a sample, right? We had an expectation. Let's go back. We had an expectation like this, and then we said, well, we don't have the expectation, but let's take a sample and minimize the loss over that sample. So we went from here to there. Cool. So how do we do that for this thing here? What's wrong? Any?
We don't have the data.
Yes, we don't have the data, right? So the expectation here is over the whole population, right? But what I do have is samples of the loss for the control population only in the control population, or the control outcome only in the control population. So that's kind of weird. And tomorrow will be about dealing with this. For now, we will just do this and hope that it works anyway. So what we will be doing is fitting lines only to the to the population corresponding to the treatment that we care about. So in this case, I've shown a line here fit to the control population. So this would be the control outcome. And what you should realize is that actually the loss or the residuals here in the blue population aren't really representative of the orange at all. So that means that this part here, you're minimizing kind of the wrong quantity if you go to a sample and look only at the control population. Okay, we'll see this mathematically later. But this is the gist of the work that I've been doing for the last couple of years. So there's no real guarantee that we have a reasonable estimate of this from that. So this is the loss over the whole population, and this restricted to the control group. Questions on this? Okay, it'll be clear tomorrow. That's not. So lastly, I'd like to finish this lecture today with a couple of notes on Kate. So I started out saying that we care about two different types of effects. The first one was the conditional average treatment effect, and the second, the population effect. Both of which you can get from these conditional expectations that we've been talking about for the last couple of minutes. So if we get tau right, the conditional effect, we also get 8 right. That's one thing. It's not necessary, but it's sufficient. So another way to think about this risk minimization problem is that we want to minimize the risk in predicting Kate, which is now the difference between the two functions and not the functions themselves. So our problem, as used to supervised learning, tau, this label that we want to be close to, is never fully observed. We only observe one of these two functions, or y0 or y1, and yeah, so we can't really get a sense of this risk either. And this is not only because we don't have, it's not only because the population is now everyone, it's just we have that quantity for no one. So that's unfortunate, but fortunately for us, and this kind of goes with intuition, is that it's enough to be good at predicting both functions fx1 and fx0. It's not sufficient, because what I drew here was essentially to illustrate that if you get the effect right, this thing here, the broadband, it doesn't matter really where you place yourself on the y-axis, which would be these two f's over here. So it's an interesting problem that I don't think has been solved fully yet, to say how can we estimate the effect well without really caring about the potential outcomes themselves. Because sometimes you only need the effect. If you want to come up with the best policy and you don't really care what is the blood sugar level 5 months from now, all you need is the effect. So if you like this sort of stuff, you should be thinking about how can I estimate that? Because it sounds like something that should be easier to estimate, or rather more sample efficient. Because typically we believe that the effect itself is a simpler function than the outcome. And the reason being that typically, the effect is a function of the treatment variable, but the outcome could be a very complicated function about everything that goes into your body, right? So yeah, think about that. Anyway. Fortunately, it can be shown pretty easily that you can bound the risk in predicting the effect through the risk in predicting the two different outcomes that we have. So I've put them here as RP0 and RP1. So this is in the expectation form, not in the empirical form. But you can carry out what would happen with standard learning theory if you were to learn these from finite science.
Is that the reverse triangle in it?
It's relaxed. Because the square loss is not a metric, so you make it's a pseudometric with factor 2. That's where you. So actually, you can see this is loose, right? We expect if this is close and this is close, we don't really expect this factor 2 here. Right. It's annoying. And another thing is that this is kind of pessimistic in that we make errors in opposite direction for these two. But maybe we believe, maybe we have some intuition that we are consistent in our errors. So that's another reason. Maybe it should be the mean of these two as opposed to twice their sum. Yeah. Okay. So what we did as first, as a first attempt in this field was to build a neural net model. This is not actually our first model, but I'll pretend it is because I like it better. So me and a couple of co-authors, Uri Shalit and David Sontag. David is the guy who runs the lab that I'm in over at IAMS. And we worked out a model like this. And it's a feed-forward type network. We have a deep neural network creating some representation. And what we do then is to split this off into two separate hypotheses, the one for the controls and the one for the treated. And then we minimize some risk. And we're still pretending like we don't have that distributional shift problem that I mentioned before. Okay, so we thought that this has two nice properties. The first one is that the representation here, the yellow box, is shared for everyone in the control and the treatment group. And the intuition being that, say you're dealing with images as your input. Now, what are the important properties of an image typically will be important both for people who are treated and people who weren't. So think about classifying the effect of something on lung cancer or something to do with the lungs, and you have X-rays of lungs as your input. Then image features are kind of, if not static, at least to a large extent, they're shared across different problems. And you know that if you've been dealing with ImageNet and pre-trained networks in various ways. The second part is that we split the outcome up, or the predictions up, for the two different groups. The reason being that we don't want to have this washing away the treatment effect that you could have if you have a variable selection procedure or something like that. So we really want to keep as much information about the treatment as possible, and you can't really lose it if you have two separate outcomes like this. So just this architecture, moving to this from something like linear models or decision trees or another very simple neural model, we have the error on a benchmark that was widely used to evaluate these types of models, causal effects explanation models. And so that was surprising to us. If you take just X and T and concatenate them and train a supervised learning model, you get about twice the error that you would with this, which was fun. But more importantly, our work didn't stop here, because we tried out some deep learning and that was fun, but we also went on to produce the first learning theory for causal effect estimation, and I will be talking about that tomorrow. So that deals with the problem that we only observe labels for parts of our data, and that in turn led to new algorithms, and that's it for me. I'll see you guys tomorrow.
No.